Hello everyone. Well, I guess this is one of the most awaited videos because interviews questions on material science I don't find it anywhere on net. So I guess this content you won't find anywhere also. Uh, so first of all, this video will be like a question answers session in which I'll be answering you the most probable interview questions in material science. Well, material science is a very vast discipline, one of the most desirable interdisciplinary subjects. So, interviews in this can go in any direction as a different stream people also apply apart from mechanical. Somewhere civil people are also allowed, somewhere polymers, ceramic. So, it's a very uh, vast discipline. Like questions can be asked from any point. But then these questions are framed considering mechanical as your background. As I am a mechanical graduate, so I have considered my background, and on the basis of that, I have framed or I have compiled these set of questions. So it will be more of a learn to question session. Obviously, not the entire subject, but yeah, after going through these questions, you'll have a pretty much clear idea about what material science deals with. Um, so there are around 65 to 68 questions at moment, and I'll update it as soon as I get more questions. So without wasting any more time, let's start with our first question. What is crystal? Okay, the answer to this can be said like crystal is a three-dimensional periodic arrangement of atoms in space. As simple as that. Next one. The second question is what is lattice? Lattice is also similar to crystal, but there is a difference. Lattice can be explained as a three-dimensional periodic arrangement of points in space. Now, moving on. How are crystal and lattice related? See, lattice and crystals are kind of similar, but there is a difference. Lattice is just a geometrical concept. Like we are talking about a 3D periodic arrangement of points. But when we talk about crystal, crystal is a three-dimensional periodic arrangement of atoms in space. So if you look at the wordings clearly, you will find I have used atoms and points. Lattice and crystal are related with motif. Another term for motif is also called as basis. Now, what is motif? Motif is uh, atom or a group of atom which are associated with any lattice point. So, in simplified version, if I tell you, it is something as lattice plus motif will give me a crystal. Lattice will tell me about how to repeat, whereas motif will tell me what to repeat. So if I combine this, I'll get a pattern. Moving on. Now, how many crystal systems are there? Well, there are 7 crystal systems. If you are asked about naming them, so I have learned them in a different manner, as in like what was considerable or suitable for me. See, I am from mechanical background. We have a subject known as HMT. So I tried learning it in a form as CTOR HMT, CTOR HMT. HMT is a subject and CTOR, like that. Where in this I can name all the 7 crystal systems in this format. C for cubic, T for tetragonal, O for orthorhombic, R for rhombohedral, CTOR, and then HMT, H for hexagonal, M for monoclinic, and T stands for triclinic. So there are 7 crystal systems. Now moving on. What is a unit cell and what are the types of unit cell? Okay. So unit cell can be understood as a region of space which can generate the entire lattice. Like how? By repetition. How do I repeat it? Using lattice translations. So it is something like you take a region of space and repeat it by using lattice translation so that you can get the entire lattice. Types of unit cell. Well, there are 2 types of unit cell. primitive and non-primitive. What are primitive unit cells? Well, primitive unit cells will have lattice point only at the corners, whereas non-primitive unit cell will have lattice point at its corners as well as some other points are also inclusive. Next, how many possible lattice arrangements are possible in a unit cell? There are 4 different lattice arrangements which are possible in a unit cell. They are primarily known as PIFC arrangements, where P stands for primitive or simple type, I stands for body centered type, F stands for face centered type, and C stands for end centered, or we call it sometimes as base centered. Now, what is P, what is I, what is F, what is C? Well, P is something as, if I say P, I mean my lattice points are only at the corners of my unit cell, definitely. Now, if I say I mean in a unit cell my lattice points are at corners, plus there is also a lattice point at its body center. If I say F, that is face centered, that means my lattice points are at corners, plus lattice point are also present at face centers. Now, if I say C, C means lattice points are at corners, plus lattice points are also present at any two opposite faces, or if I say opposite faces, I might use as parallel faces also. Like take a pair of faces which are parallel and place a lattice point at the face centers. That's all, apart from lattice point at the corners. So in these ways we can get different lattice arrangements in a unit cell. So if I say cubic P, it means my unit cell is a cube, cubic P, as in like primitive or simple cubic. So my unit cell is a cube with, in primitive I told you lattice points are present only at corners. So a cube with lattice point only at corners. If I say cubic I mean a body centered cubic, BCC. Now in this, obviously my lattice points are at corners, plus one point at its body center. I hope it's clear. Moving on. Now, what are lattice parameters? Okay, so lattice parameters are nothing but length of the 3 edges of unit cell. If you take a unit cell, the length of the 3 edges, or you can also say it is the length of the 3 basis vectors and all the 3 interaxial angles between them, like A, B, C, alpha, beta, gamma. These 6 are the lattice parameters. Okay, moving on. What is the reason for classification of lattice into 7 crystal systems and 14 Bravais lattice? The reason for classification of lattice into 7 crystal systems and 14 Bravais lattice is lattices are, in simpler terms, if I say, it is symmetry. Okay, now why 7 crystal systems and why 14 Bravais lattice? Well, lattices, if I look on the basis of point groups, then there are 7 point groups possible. In other words, there are 7 different rotational and reflection symmetry which are possible, and this is what we call as 7 crystal systems. Now if I look at from space group point of view, then there are 14 different space groups, or in simpler terms 14 different kind of complete symmetries are possible, and this is what we call as 14 Bravais lattice. But if simply asked, the reason for classification of lattice into 7 crystal systems and 14 Bravais lattice is symmetry. So obviously if you talk about symmetry, the next question will be, what do you mean by symmetry? Well, an object is said to be symmetric with respect to some operation. If I say my object is symmetric with respect to some operation, then it means that it can be brought into self-coincidence by using that operation. Means, if I tell you in simpler terms, if with respect to an operation, if I get same thing, that is self-coincidence, then we call the object symmetric with respect to that operation. Okay. Moving on. Now, what are point groups and space groups? Well, not much about this is into our syllabus, but sometimes it is asked. Since we talked about, on the basis of point groups, the classification as 7 crystal systems, on the basis of space group, the classification as 14 Bravais lattice. So obviously there will be a cross question. Okay, what are point groups and space group? In simpler terms, all non-transitional or point symmetries, whatever are there, if we combine them and form a group, then it is known as point group. And space group, if I tell you, it is something like a group of all symmetry operations. Like all symmetry as in total symmetry. Total symmetry means including translational symmetry as well as point symmetry. So if I form a group, that is known as space group. Obviously, I cannot explain you need to have a prior knowledge about rotational symmetry, translational symmetry, point symmetry. So I guess you guys know about that, so only I'm answering with respect to that. Okay, moving on. What is planar density and what is linear density? Well, planar density is number of atoms centered on a plane with respect to area of the plane. It tells you about how densely a plane is packed in simpler terms. So what is the formula for this? Well, the formula is number of atoms centered on a plane divided by area of the plane. Now similarly, if I'm talking about a plane, I use the term planar density. Now if I'm talking about a direction or a crystallographic direction, in that sense I talk about linear density. So similar to planar density, linear density is also defined as how densely a direction is packed. Well, if you ask me the formula is number of atoms which are centered on the direction vector with respect to the length of the direction vector. By what direction vector am I talking about? You guys can relate to Miller indices of directions from that. See, why these two terms are important? Because the properties of a material in general will depend on linear and planar densities. Example, a very common example for this is slip. Well, slip will occur on planes that have greatest density of atoms, also in those directions which have highest density. Means highest density planes and in highest density atoms, in that direction only slip will happen. So now slip controls my plastic deformation, so that controls different properties such as ductility and all. So in that way we can say properties are generally dependent on these two variables, linear density and planar density. So we need to study them. Now moving on, what is the maximum value of atomic packing fraction and is it possible to have 100% packing efficiency? Well, the maximum value of atomic packing factor is 74%, that is 0.74. And well, is it possible to have 100% packing efficiency? No. Why no? Because we assume that atoms as hard solid spheres. Now, according to Kepler conjecture, the maximum packing efficiency for this highest possible packing efficiency which we can achieve is 74%. So it is not possible to have 100% packing. Don't go into research like what is Kepler conjecture and all, but it's something like if you pack spheres, the maximum possible efficiency what you can get is 74%. Moving on. Well, now this is a very good question. It's a simple question, but it's kind of playing with you, with your words actually. Now, atomic packing factor tells you how densely a unit cell is packed, right? So in some way we are talking about density, right? So the density of FCC and HCP both are 74%. So I mean the atomic packing factor of HCP and FCC both are 74%. Then does that mean ki density of FCC and HCP is also 74%? Well, no. So they have asked why zinc, that is HCP, and copper, FCC, have different densities. Well, we are comparing two different unit cells. Zinc is a hexagonal closed packing. That means the unit cell is hexagon. Whereas in case of copper, which is FCC, that is face-centered cubic. I'm talking about a cubic unit cell. So you cannot compare two different things, right? So you cannot talk about that. So it's a vague question. It's just like playing with your words. Like if you tell atomic packing factor tells you how densely a unit cell is packed, then they'll try to play like this. Moving on. Which is more ductile, FCC or HCP? Well, face-centered cubic, FCC, is more ductile as compared to HCP. The reason for this, well, the number of slip systems are more in FCC as compared to HCP. What are slip systems? What are slip systems? We'll see later. Like if it is asked, obviously it will be asked. It's a see, this kind of questions which is more ductile, FCC or HCP, this will be like interlinked. Obviously, if you're talking about FCC is more ductile, you should know why. Then you say that okay, because of the presence of more number of slip systems, FCC is more ductile. In that case, a cross question comes. Okay, since you have spoken about slip systems, that means you know slip. That means you know slip systems. What are slip planes and also that might be cross question on these. So we'll see if that is asked. Moving on. Name some elements which have FCC crystal structure. Well, gold, silver, copper, nickel. I'll tell you a simple trick. How I used to learn this. See, what I realized was whatever is costly, that comes under FCC. FCC is highly ductile, and whatever is costly, that comes under FCC. So, say gold is costly, silver costly, copper costly, nickel costly, aluminum costly. So all these have FCC. So you can just learn in this way, as in whatever is costly, that is FCC. In simpler terms, not all, but in general. Moving on. What is slip? Well, I told you there will be a cross question at some point. So what is slip? Well, slip can be defined as a unit plastic deformation in simpler terms. I guess this is enough to make it clear. This is clear enough. Unit plastic deformation is called slip. Moving on. What is a phase? Well, phase. Professor Raghavan in his book has explained phase beautifully in just 6 words. He tells us phase is physically distinct, chemically homogeneous, mechanically separable state of matter. That's it. Physically distinct, chemically homogeneous, mechanically separable. 6 words, that's it. What is phase diagram? Well, phase diagram is nothing but it's a plot. It's an equilibrium diagram, that is different, but it's a plot. It's a plot between temperature and percentage composition. And you see, I guess every one of us have seen a phase diagram, so we can tell what is there. It's a plot between temperature and percentage composition, and in simpler terms, it tells you about the stability of phase at different temperatures and composition. Like what phase will be stable at what temperature and what composition. That is evident from phase diagram. Simple as that. Just you look at the phase diagram and tell what it is containing. It tells you about what phase is stable at what temperature and what composition. Moving on. What do you mean by solid solution? Okay, so now we are entering phase diagrams. Well, solid solution, when 2 elements combine together to produce a single solid phase, we call it solid solution. It's something like solid ka solution, like they exist in a single solid phase. They are stable actually in a single solid phase in simpler terms. Now, there are 2 types of solid solution later we'll study, like interstitial solid solution and substitutional solid solution. That if asked types of solid solution, you can answer 2 types, substitutional and interstitial. Moving on. What is an isomorphous system? Well, On the basis of solid solubility, we characterize, or we say, phase diagrams are of three types: isomorphous, partial eutectic, and eutectic. So isomorphous is when these two elements which are combining to form an alloy, they are completely soluble in liquid as well as solid phase. That is isomorphous. Means, see, if you look at partial eutectic and eutectic, the only difference, see, they will be completely soluble in liquid phase, but the difference lies when we talk about solid solubility. So if they are completely soluble in solid phase, that forms isomorphous. If they are completely soluble in if they are partially soluble in solid phase, that is partial eutectic. If they are completely insoluble, that is eutectic. So if asked about isomorphous, it is two elements which are combining to form an alloy. They are completely soluble in liquid phase as well as solid phase. What is an example of isomorphous system? Well, copper nickel phase diagram, that is a very popular example of isomorphous system. Moving on. What is Gibbs phase rule? Okay, Gibbs phase rule is Gibbs phase rule is P plus F is equal to C plus 2, where P stands for number of phases, F stands for degree of freedom, C stands for the components involved. So basically, we use this Gibbs phase rule to find out degree of freedom actually. Also, see, generally all our phase diagrams are plotted at particular pressure. So we do not go for this Gibbs phase rule, we go for a modified version of this Gibbs phase rule, and the modified version is nothing but P plus F is equal to C plus 1. See, there is a simple way to learn this. What I tried was, I remember KFC. So similarly, I used here PFC. So that will be in your mind. P is phase, F is degree of freedom, C is components. Now, moving on. Mention one limitation of lever rule. Lever rule is used to find the compositions of different parts, like liquid plus alpha is there, different phases are there, then what part is, how much weight percent is, how much fraction is liquid, how much fraction is alpha, and so on. So there is one limitation to lever rule. The limitation is actually lever rule can only be applied to binary systems. You cannot apply it to ternary phase diagrams and all. Moving on. Tell us about Human-Rothery rules. Well, Human-Rothery rules. See, actually, Human-Rothery rules are a set of rules in order to obtain complete solid solubility. Okay. There are 4 rules actually. First, in order to obtain complete solid solubility, the crystal structure must be same. Second, the complete solid solubility will be exhibited by pair of elements which have atomic radius similar, or a variation of 15% in atomic radius is allowable. Third one, their electron negativity and electron affinity must be comparable. Also, fourth one, the this valency should be same. Okay, so if these 4 rules are satisfied, then what you get is complete solid solubility. Moving on, 24. Okay, so what do you mean by invariant point? Name some invariant reactions. Invariant point simply means that the degree of freedom is 0. See, what degree of freedom are we talking about? Well, if you use that Gibbs phase rule, and for somewhere if you find F is equal to 0, then that is a invariant point. Name some invariant reaction. Well, some of the invariant reactions are eutectic, eutectoid, peritectic, peritectoid. Question number 25. I suppose eutectic, eutectoid, peritectic, peritectoid must be clear to all of you. Uh, Obviously, if you have studied iron carbon phase diagram, you must be knowing what is eutectic, eutectoid, peritectic, peritectoid, and so on. Now, I'll tell you an important fact about peritectic reactions. See, peritectic reactions appear only mostly in those phase diagrams where they have a huge difference of melting points. So, if you look at melting point of iron, it is somewhere around 1500 something. If you look at carbon, it's somewhere around 4000 or something, or 5000, I don't know, something like this, but there's a huge difference, right? So in whatever phase diagrams these peritectic reactions appear, those phase diagrams are known as peritectic phase diagrams. So now moving on to this question, is it iron carbon, or is it more appropriate to call it iron cementite phase diagram? Well, it's a very general interview question. If you are asked phase diagrams and if you are asked iron carbon phase diagram, I suppose this is a must question which you will face. So, well, it is more appropriate to call it iron cementite phase diagram rather than iron carbon phase diagram. Why? Because you see, on the composition axis we go up to 6.67% and stop and say this much solubility is only possible, right? So now if it was iron carbon, then I would have gone up to 100%, but since it is up to 6.67%, it is more appropriate to call it iron cementite, because we are going up to 6.67% only. Also, more than 6.67% carbon is not soluble, so it is more appropriate to call it iron cementite phase diagram. Draw iron cementite phase diagram. Well, yeah, you can be asked to draw iron cementite phase diagram also, so I guess I'll leave that. But yeah, that is one of the important questions that can be asked in any interviews, so I guess you should prepare with that also. You should be ready with, you should know how to draw this, and the various compositions and important temperatures and all the different reactions, because this diagram contains eutectic, eutectoid, peritectic reactions. All 3 points you should know, invariant points, and so on. Moving on. Okay, yeah, why only till 6.6% do we show on iron carbon phase diagram? Well, the maximum solid solubility of carbon in iron is only 6.67%, so we show up to 6.67% only. Simple. Moving on. Okay, yeah, this is a good one. Copper nickel phase diagram we draw up to 100%, but in iron cementite only till 6.67%. Is there a limit of solubility? Okay, yeah, so this is a very good question, because what we're talking about is a limit of solubility. See, if you remember a copper nickel phase diagram, we go up to 100%, but in case of iron cementite phase diagram, we go up to 6.67% only. So the question what he wants to ask is, why this? Is there some limit, like is there some difference between these two phase diagrams? Well, yes. See, copper and nickel, they form substitutional solid solution. So in that case, it's like, in case of substitutional solid solution, the the solute atoms will come and replace the solvent atoms. Okay, and like whatever comes, it substitutes one atom and replaces it, and this goes on. So obviously, if there is a replacement of atoms from their lattice points, so complete replacement is possible. Means, say if A and B are there, B comes and replaces A, so this can be possible up to 100% removal of A, and only will have B. But iron carbon is an interstitial. Carbon in iron forms an interstitial solid solution. Now, interstitial solid solutions are those in which the solute atoms occupy the void spaces. means the interstitial voids, not their lattice point, not their actual spaces. So they go and sit between the these voids, at voids. So now if they sit at voids, so just think, if obviously the number of voids in the entire lattice will be limited. So once these voids are filled, no more carbon can come and sit at those places. So we say there is a limit of solubility. When we are talking about interstitial solid solution, there is a limit of solubility. So in simpler terms, if I tell you to understand, copper nickel, they form a substitutional solid solution. So there is no limit of solubility, as this substitution can move from 100%, from 0 to 100%. But in interstitial solid solution, since the atoms will come and occupy the void spaces, and void spaces are limited, as these void spaces are limited, so interstitial solid solutions can never have 100% solid solubility. So we can say there is a yes, in case of interstitial solid solutions, there is a limit of solubility. I hope this is clear. Now, what are defects in crystals? Well, defect is nothing but deviation from the perfect crystals. Now, these defects will control various properties also, both physical as well as mechanical. Now, these defects are classified as zero. We know there are zero defects, zero-dimensional defects, or popularly known as point defects. Example: vacancies, interstitial voids, Frankel defect, Schottky defect, and so on. There are one-dimensional defects. One-dimensional defects are also known as line defects. Examples: dislocation. There are also two-dimensional or plane defect, or sometimes these are also known as surface defects. The examples for these are free surface, grain boundaries, twin boundaries, stacking fault, etc. Moving on. What is Frankel defect? See, in case of Frankel defect, what happens is my atoms from my lattice, it moves from there and goes and sit into the interstitial voids. Okay, so thus I have created a vacancy as well as I have an interstitial occupancy. This is Frankel defect. Means if I have a lattice, then one of the atoms from the lattice moves from its original lattice point and goes and sits at the interstitial voids. Sorry for the disturbance. Now, what is Schottky defect? Well, Schottky defect is nothing but when a pair of cations and anions go missing in pairs. Means two. Means one cation goes missing and one anion goes missing from my lattice point. That is known as Schottky defect. It is also a point defect. What are dislocations? Well, dislocations are one-dimensional linear defects. What are the types of dislocations? Well, dislocations are of three types: edge dislocation, screw dislocation, and mixed dislocation. Mixed dislocations are like a mixture of both edge and screw dislocations. Next question: if you know this much about dislocations, obviously you must be knowing how do you characterize dislocation. So the answer to this is very simple. Well, every dislocation is characterized by two characteristic vectors. One is my tangent vector, another one is my Burgers vector. Okay, so like tangent vector is nothing but it's a line vector. It is a line vector, say it's a unit vector which is perpendicular to the dislocation line. So we sometimes neglect it and it does not play much of a role, but so mainly we say like we characterize the dislocation using its Burgers vector. Well, how do we characterize it? If my Burgers vector is perpendicular to the dislocation line, I call it edge dislocation. If my Burgers vector is parallel to dislocation line, I call it screw dislocation. And if my Burgess vectors is inclined to this dislocation line, then we call it mixed dislocation. Okay, moving on. How do you increase strength of a material? Tell about various strengthening mechanism. See, in general, if I say dislocation is responsible for increasing strength of a material. How? Well, it's the dislocation interaction which sometimes affect the strength of a material. There are different ways of increasing the strength of a material. Various strengthening mechanisms include, first of all, alloying. Okay, how it creates a barrier is if you alloy, like if you form an alloy, obviously you are using two metals, or in that case, the foreign element will come and sit at the grain boundaries. Or if it's a substitutional alloy, then I'll leave it. I can explain it in this way, like if alloy, sorry. Well, in simpler terms, see, I am confused how to explain this to you. Well, okay, yeah, we'll go in this way. See, alloying, it can form a substitutional solid solution or an interstitial solid solution. In that case, if it's a if my lattice, like if my alloying atom is a substitutional one, in that case, it will substitute. Now, it depends whether my wherever it is substituting, whether the size of my atom is large or small. If it is small or if it is large, in both case it will generate a strain field. Now this strain field will act as a barrier in movement of dislocations. There are different ways. One of them is alloying, another one is grain size reduction. See, as the grain size is reduced, by Hall patch equation we can say the strength of a material will increase. Also, there is what do you call strain hardening, that is most common way. See, this can go very deep. Like if question is getting started to be asked on this topic, it can go very deep. So I suppose you can answer in another way, that is it is the dislocation interaction which controls the strength of a material in one or another way. How? If a dislocation is interacting with dislocation, it results in strain hardening. It is one of the cause of strain hardening. So in that case, strain hardening is a strengthening mechanism. If you increase the number of grain boundaries, so dislocation will have to cross more grain boundaries, there will be more obstacles in the path of dislocations. In that case, you will need to apply more stress. So in that case also the strength increases. Moving on, what are slip systems? See, dislocations move in certain crystallographic planes and in certain crystallographic directions. This combination of slip planes and slip directions is known as slip systems. Dislocation cannot move in any plane. Dislocation can only move in a closed back planes only. Okay. So obviously the next question will be, why does slip occur only in closed packed planes only? See, slip occurs in closed packed planes only because the dislocations find it easier to move in these closed packed planes. See, also you can explain it as in closed packed planes. See, also, yeah, this is a better explanation. The stress required to move a dislocation is dependent on the length of Berger vector. Now, if my plane is closely packed, the length of Berger vector will be less. So, less length of Berger vector implies that less strength is required to move my dislocation, and so if my plane is closely packed, I will require less stress. So, slip will occur in a closed packed plane only. What is the cause of strain hardening? Well, I explained this before. The cause of strain hardening is dislocation interaction with dislocation, another dislocation. And if you want to explain more, you can say when a dislocation encounters a dislocation forest, in that case there is a repulsion, and now this dislocation has to overcome this dislocation forest in order to move, thereby causing the phenomena of strain hardening. Which law we use to relate stress and strain in plastic region? Well, this is a very simple one. We go for power law, also known as the Holomann's law, Holomann's curve, which relates sigma true is equal to k times epsilon true to the power of n, where n is the work hardening exponent, k is the strength coefficient. Sigma true and epsilon true are true stress and true strain respectively. Moving on, which is more ductile, coarse grain or fine grain? Coarse grain is more ductile. Why? Well, coarse grain will have larger path to move to grain boundary. Like dislocations, while moving, they'll have to cover larger path while they encounter a grain boundary. So the distance through which they travel, that will increase. Now, if they get to travel more distance, then we'll get more time, or say will get more time means my material will show plastic deformation for more time. So it is an indication of ductility also. So we say that coarse grain is more ductile as compared to fine grain, because if we are getting more time, then the material will show plastic behavior for more amount of time. In that case, coarse grain is more ductile. What are the possible dislocation motions? Well, there are three possible dislocation motion. One of them is glide, one of them is climb, another one is cross slip. Not every material shows upper yield point and lower yield point. How do you find yield point in that case? Yeah, well, not every material will show upper yield point and lower yield point. That is true. Mild steel shows this phenomena, whereas in case of aluminum, we don't find any yield point. In that case, what I do is I use 0.2% offset strain method in order to calculate my yield point. See, this is an example. This is how you do it. As you can see, it's a plot between stress and strain, and you cannot see any upper yield point and lower yield point. So this is this is a stress strain curve of aluminum, I guess. So what I did, I used the 0.2% offset strain method. In this, what I do is add 0.2% strain. Now, when I talk about 0.2%, I mean the value as 0.002. At that value, I draw a line parallel to the elastic line, like the basic curve. Wherever it cuts the stress strain curve, that point gives me my yield strength. Okay, I guess this is simple. Moving on. Yield strength of most metals decrease with increase in temperature. Yes, this is also true. See, yield strength of most metals decrease with increase in temperature. Why? Because at high temperatures, uh, the atoms are more vibrating. In that case, if I say the atoms are more vibrating, they have thermal agitation, means they have more energy. So it becomes easier for dislocation to move at higher temperature. So yield strength decreases. So see, this yield strength decrease is a secondary effect of increase in temperature. The primary effect is the elastic modulus decreases, so my yield strength also decreases. Moving on, how many phases of iron are there? Well, there are 5 phases of iron: alpha iron, gamma, delta, martensite, and cementite. See, this cementite is a metastable phase, martensite is a non-equilibrium phase, but still there are phases of iron. Alpha is ferrite, delta is ferrite, gamma austenite. Why martensite? Now, this is a very popular question. Since you know iron carbon phase diagram is definitely asked, so another question which comes up is why martensite is not visible in iron cementite phase diagram. Well, the answer to this is very simple. See, martensite is these phase diagrams are equilibrium diagrams, whereas martensite is a non-equilibrium structure. Martensite is a non-equilibrium phase. So obviously on an equilibrium phase diagram, I cannot show something which is non-equilibrium. So martensite is not visible. What is the crystal structure of austenite, cementite, and martensite? The crystal structure of austenite is FCC, cementite is orthorhombic, and martensite is body-centered tetragonal, PCT. Name some heat treatment process. Annealing, normalizing, tempering, hardening, all these are heat treatment processes. Why do we go for these? To obtain desirable properties. Sometimes we need hardened surface, we go for hardening. Sometimes we need to relieve stresses, we go for annealing. If you don't want to see, normalizing is also known as final heat treatment process, because in this we get outer surface as hard, whereas the inner core is still soft. So we get both kind of properties, that is hard as well as like brittle, as well as tough core and hardened surface. So that is also known as final heat treatment processes. Now moving on. Is TTT curve and CCT curve same? If not, is there any difference? So TTT stands for temperature time transformation curve, and CCT stands for continuous cooling curve, continuous cooling transformation curve. Well, they are not same. Yeah, there is a difference. So the difference is the name itself. Temperature time transformation, I can hold my specimen, whereas in case of continuous cooling transformation, the name itself suggests it's a continuous cooling curve. So I cannot hold. When I cannot hold, my bainite can never be produced in CCT curve, whereas in TTT I can produce bainite. When I'm talking about obviously iron. What is creep? Which is better creep resistant, coarse grain or fine grain? Okay. Creep can be defined as time dependent permanent deformation of material at high temperatures at constant load or stress values. Okay, so it's a permanent deformation of material at high temperatures, which is time dependent. So generally creep occurs at high temperatures above 0.4 Tm. Okay. Now what is which is better creep resistance, coarse or fine grain? Well, coarse grain are better creep resistance, as the number of grain boundaries in coarse grain are less, so chances of grain boundary sliding decreases. So coarse grain are better creep resistant materials. Now, which is better fatigue resistant, coarse grain or fine grain? Why? Well, if you talk about fatigue failure is characterized by three distinct steps. That is, crack will initiate, crack will propagate, and then final failure. Okay, so fine grain is better fatigue resistant. Why? Because in fine grain the number of grain boundaries are more. Now these grain boundaries act as obstacles in the movement of this crack, so increasing the fatigue resistance. I hope this is clear. Moving on. What do we add in iron to increase its corrosion resistance? 52 questions. That's a long way to go. Well, yeah. Moving on. What do we add in iron to increase its corrosion resistance? Well, we add chromium. Chromium is an alloying element which we add in iron to increase its corrosion resistance. Chromium forms a protective layer at the grain boundaries. Obviously it's a foreign element, so it will be accommodated at the grain boundaries, so it forms a protective layer of chromium oxide, Ci2O3, which protects from corrosion. Okay, yeah, this is again a beautiful question. Copper has 3 times corrosion resistance than chromium. Still, why do we go for chromium? Well, this has a very interesting answer. See, there are sometimes we just don't look into better properties, but also we look into the cost associated at obtaining those properties. Copper is a costly material as compared to chromium, so we go for chromium even though copper is 3 times corrosion resistant than chromium. Here the cost factor comes into play. Name austenitic phase stabilizers and ferritic phase stabilizers. Okay, austenitic phase stabilizer is nickel and ferritic phase stabilizer is chromium. What is hardness? Well, hardness is a measure of material resistance to localized plastic deformation. Okay, so there are hardness tests where, like, generally we use different numbers like Brinell hardness, Wicker hardness, Knoop hardness, or Rockwell hardness sometimes to measure these. What is the hardness and all? We represent it using numbers. Okay, what are composite materials? Well, yeah, composites are combination of 2 or more materials. Okay, like one of them is matrix, another one is reinforcement. See, general, each of the materials what we are using, both must exist more than 5%. Okay, there are 2 different phases. One is matrix, which is the continuous phase, and another one is the reinforcing, which can be continuous or discontinuous both. So basically composites, why do we go for composites? Because I want better properties. Okay, so that's why we are going for combination of two or more materials. Okay, yeah. What is mar tempering? Mar tempering is also known as stepped quenching. So what I do my quenching in steps. Why do I do this? To minimize the temperature gradient between surface and core. See, obviously the surface as well as the core, they will be exposed to different cooling rates. So now what I quench for some time and then I stop. I wait till my surface and core have attained the same temperature and then I proceed with my quenching. So this kind of quenching is also known as mar tempering. You can see it's kind of quenching in steps. I wait for my surface and core to attain same temperature and then proceed. Yeah, next one. What is toughness? The total strain energy absorbed up to fracture, or area of stress strain curve up to fracture. That can be explained as toughness. What is ductility? Well, ductility, basic definition everyone knows. It is the ability of a material to be drawn into wires, I guess, yeah. And in also ductility is a measure of, like, it tells you about the degree of plastic deformation possessed by a material. So generally, if your plastic deformation is less than 5%, we call the material as brittle. If it is more than 5%, we call it ductile. What is resilience? Well, the strain energy absorbed up to elastic limit is known as resilience. Now there is also a term known as proof resilience. Proof resilience is till, like, if I like the maximum strain energy till elastic limit. So I'll consider up to elastic limit. If I talk about resilience, it is within elastic limit. Sorry, yeah, resilience is within elastic limit. So any point if I take within elastic limit and I find the total strain energy up to that point, and that is resilience. But if I talk about proof resilience, that is the maximum value of resilience in elastic region. What is hot shortness? Well, this is also known as some sulfur embrittlement. See, sulfur is sulfur is present in almost everything in this nature. So obviously iron has sulfur impurity. Now this sulfur combines with iron to form iron sulfide. Now the melting point of iron sulfide is low. Obviously iron sulfide, being a foreign element, will be deposited at the grain boundaries. Why? Because the voids at grain boundaries are larger as compared to the interstitial voids and so on. So these iron sulfide deposited at the grain boundaries, since the melting point is low, when we do warm forming, or like when we expose this iron to higher temperatures, these iron sulfide evaporates or melts away, leaving cracks. This is known as hot shortness. How do we remove this? For this we add manganese, Mn. So before sulfur could capture iron, manganese captures sulfur and form manganese sulfide. Now this manganese sulfide has high melting point. So obviously being a foreign element, it will be deposited at grain boundaries again. So this, since it can withstand high temperatures, so this phenomenon of hot shortness is removed. Now also there is a property of this manganese sulfide, it has very good machinability, thus it increases. So manganese addition also helps in increasing the machinability of iron. Okay. Next one. What is the percentage of carbon in steel and cast iron? Okay. Steel, the carbon percentage is limited up to 2.1%, and anything above 2.1% up to 6.67% is cast iron. As per the hypothetical iron carbon system. Well, obviously there are iron. We all know that pure iron carbon system is hypothetical. There will be some impurities, so it varies. But in general, if someone asks you, we can say up to 2.1% is steel, and more than that is cast iron. Yeah, this is a very good question. Are dislocations present in amorphous materials? Well, no. See, these dislocations are one-dimensional linear defects, and they have arisen in because of some difference in periodicity or arrangement of atoms. And in amorphous, since there is no order, it's highly disordered, so there's no chance of being dislocations being present. Draw stress strain curve for aluminium. Well, this is the stress strain curve. I guess I've shown this before also. Here this is 0.2% strain. Again I'm talking about 0.2% strain. 0.2%, that is 0.002. Okay, here yield point is not upper yield point and lower yield point is not visible, so we go for this 0.2% offset strain to find the yield point. What are thermosets and thermoplastics? As I said, material science is an interdisciplinary branch, so obviously you can be asked these questions also. What are thermosets and thermoplastics? See, how I remembered these is plastic can be melted, right? So thermoplastics are those which, if they are set or cured for the first time, they can be again remelted and remolded or reused. Whereas thermosets cannot be reused or remelted after they had been cured once. So these are only used once. So plastic can be remelted, so it is, you can remember in this way that they can be remelted. So thermoplastics are those which can be remelted and reused, whereas it's a kind of polymers. Thermosets, once it is set, it cannot be reused. Give some examples of crystalline and amorphous materials. Well, crystalline, most of the metals are crystalline. Examples: sugar, uh, general metals like aluminium, gold, copper, anything that is crystalline. Amorphous: rubber, glass is amorphous. Yeah. What is Curie point? Well, Curie point, it's a temperature above which iron loses its magnetism. What is equicohesive temperature? Yeah, this is a good question. Equicohesive temperature is a temperature at which the strength of the grain and grain boundaries are equal. See, generally grains and grain boundaries, their strengths are different. Okay, generally if you talk about this equicohesive temperature, then in general I guess strength of grains is less as compared to grain boundaries. At higher temperature, what happens, these grain boundaries become weaker than the grain, and so these grains can slide past each another due to shear stress. Now at the temperature when these both are of equal strength, we call that temperature as equicohesive temperature. Note, this is different from ductile to brittle transition temperature. Ductile to brittle transition temperature occurs mainly because of rapid or rapid cooling, like sudden change of temperature. So a ductile material also fails as a brittle, but this is different. That's all, I guess. If you have some queries or if you want some clarifications regarding these questions, you can anytime contact me. You can WhatsApp me on 8826061626, or you can mail me your queries and doubts on iamrishav2@gmail.com. I guess this will give you a brief idea of how material science interviews are meant to be, like what kind of questions they ask. I guess this would help. If you like it, please share so that everyone can benefit from it. Thank you.